Good morning, everyone. You may have noticed people wearing these red poppies. So today, as you may know, is Remembrance Day. And for those of you new to Canada, let me just say that this is a holiday aimed at remembering those who passed away in Canadian wars, our veterans. And in particular, the poppy tradition comes from the First World War, or the Great War as it is called here, where a large number of Canadian soldiers laid their lives in Flanders fields in what today is Belgium. And so throughout the country, there's memorials in their honor. And in keeping with tradition, today at 11, we will observe a minute of silence for remembrance of these fallen heroes. So I have a timer here, and at 11 it will buzz, and at that point I will stop for a minute. So we're continuing today with our program of chipping away at our condensed matter theory of everything. Last time I showed you how the Hamiltonian that described both the lattice and electron degrees of freedom can be separated to treat electrons and ions separately. And what's the program for the next few lectures is to first focus on the electron Hamiltonian, which I wrote here in a slightly different form, but equivalent meaning as before. And specifically, the first task will be to understand the simplest possible case where electrons are simply moving on a background of uniform positive charge. So we take the ionic lattice and forget about its discreteness. We just spread the positive charge around, and this is called the Gilliu model, the simplest possible model of an electronic solid that you can write down. And the generic Hamiltonian has the following form. Basically, this first term is a kinetic energy, and it can also contain some single body potential, such as potential energy of a single electron. And then there's interaction term, which contains two electron coordinates, and this can be Coulomb interaction or maybe some more complicated two-body terms. Now, before we can address this problem, I will spend about half of today's lecture, maybe more, in developing this formalism of second quantization, which is absolutely essential to do any sort of calculation in many-body physics efficiently. Now, if you look into Ashcroft and Mermin, it does not have second quantization, which I think in retrospect is the largest shortcoming of that otherwise almost perfect book. This was written more than 40 years ago, and at that time, this formalism was known, but maybe not as widely used as it is nowadays. These days, if you go to any sort of research article in condensed matter or general many-body physics, they always use second quantization, so I will introduce it today. Now, it's a kind of very useful tool, as we will see, and it's relatively easy to state. However, its derivation is kind of subtle and tricky. Many books that you open do not do justice to this and just derive it in a kind of ad hoc way. So what I do in the long version of this course that I give at UBC, I spend actually a lecture and a half on this formalism, just to give you some appreciation what goes into it. I don't have time to do that here, so I will just give you a synopsis so that maybe you get a glimpse of this formalism. It's done nicely in this book of Fetter and Waleczka called Quantum Many-Body Systems, and I have copied the appropriate chapter here, and I will distribute it around. Now, I made only 11 copies because it seemed like it's like 15 pages, so I didn't want to waste too much paper. So I like you to share this during the lecture, and maybe 3 people to a copy. And those of you who would like to study this in more detail, please take it home. If there is more copies needed, I'm happy to produce more copies. I just didn't want to make 30 copies and then 20 will stay here and I will trash them. So let me just basically go. So a good option would be to put the PDF file. Sure, yeah, and we can do that. So basically, second quantization transforms this Hamiltonian, whose main feature, once again, is that this n is astronomically large. This n is on the order of 10 to 23. So there is 10 to 23 electrons to deal with, and rewrites it in a more efficient way. And specifically, what we're interested in is solving the Schrödinger equation. And I write it in its time-dependent form. With this particular Hamiltonian. And again, the issue here is that the number of degrees of freedom here is huge, right? And these will be, in general, in three-dimensional space, but I will often neglect to write these vector signs just to save myself writing. Okay, so second quantization here. And this is a kind of very deep development that one can credit to people like Jordan and Wigner and Fock back in the early days of quantum mechanics. Is basically a transformation on this Hamiltonian into so-called occupation space basis. And second quantization is kind of a misnomer. This Schrödinger equation here is as quantum as it gets. So we're not really quantizing anything again. I couldn't really find out what the historical connotation was, second quantization, but it's widely used. But remember, we're not really quantizing anything at this point. This is a quantum theory to begin with, and we're just going to rewrite this Hamiltonian in a different basis. Okay, so the first step in this procedure is to choose a particular basis for the expansion of these time-dependent wave functions. And typically, we choose a single particle basis that in this system, the convenient basis is that of non-interacting electrons in a box. Okay? Or these, in principle, could be bosons. It works both ways. So we choose single particle wave functions. And we call these, in keeping with this notation, psi E of k of Rk, where this E of k is the complete set of quantum numbers describing the state. So for instance, if these are particles in a box with periodic boundary conditions, maybe spin 1/2 particles, this denotes the momentum quantum number and spin quantum number. Okay? However, it might be more convenient to describe this system in a basis of harmonic oscillator wave functions. For instance, if your many-body system is a system of cold atoms in a trap, then you have this this trapping potential, which is harmonic. So this would be then the quantum numbers of the harmonic oscillator, right? You can use any convenient basis here, but the point is it's a single particle basis. And in this basis, one can write this many-body wave function as follows. We just do a usual expansion. E1 prime, En prime, C E1 prime En prime T psi E1 prime R1 psi En prime Rn. Now, if you ask me why am I putting primes on this En, it's just in keeping with the notation in this book. These are dummy variables, so I can call them whatever I want. And at some later step, which I maybe will not explicitly show here, one will do some summation here, and those primes will disappear. So sorry for the buzzing. Once again, this is the 11 o'clock. So I will pause for about 1 minute, and we will, in silence, remember our fallen heroes from many years ago. Okay, so thank you for joining me in this observation. Let's just continue. So, and again, I'm just giving you the synopsis of the main ideas in this derivation because I want to be done in relatively short time and just give you the basics and the appreciation for what this formalism is about. So the next steps I just described in words. What you do now, you take this expansion as usual, plug it into this a Schrödinger equation. You multiply from the left with the Hermitian conjugates of these wave functions. You integrate over all the R coordinates so that these wave functions drop out, and you get an equation for these coefficients C, right? Just as usual. So we substitute, integrate over Rk and obtain equation for C E1 En T, and this. There's no approximation. This set of coefficients contains precisely the same information as the wave function, because at any time you can reconstruct the wave function by just using this expansion again. And it is at this stage when the treatment for fermions and bosons starts to diverge. So this Hamiltonian can describe either fermionic particles like electrons or bosonic particles like atoms in a cold atom trap, or helium atoms in a fluid. And we have to distinguish because the two have different properties when under exchange, which reflect then in the properties of these solutions. So bosons versus fermions. And the distinction at the level of the many-particle wave function can be summarized like this. If you take a wave function and you interchange two particles, R and J, then upon this interchange, you get the same wave function up to an overall sign. And the positive sign, of course, is relevant to bosons. and the negative sign is relevant to fermions. Now, such an innocuous change has profound implications for the many-body ground states that one can obtain in this situation. And it also has implications for this set of coefficients C here. Okay, so let's discuss that now. So what one gets from looking at this is that this expression for the wave function is one-to-one correspondence with the following expression for these coefficients. So once again, at the level of these coefficients, exchange of two particles corresponds to exchanges of the two sets of quantum numbers. And again, the coefficient is either symmetric or antisymmetric upon that exchange, depending on whether particles are fermions or bosons. And one could just check that by comparing the two expressions. It's almost trivial. So let me, from now on, for a while, focus on bosons, which are somewhat easier to treat, and then we will see how to treat fermions with some modifications. Okay? Any questions right now? And here we come upon there's two key ideas in this construction, and we're now coming upon the first of those two key ideas, namely that because of for bosons we have this plus sign, so that tells us that we can rearrange these quantum numbers basically at will, right? If we interchange two of them, then nothing really happens. These coefficients remain the same according to the symmetry property. And this is fundamentally related to the fact that these quantum mechanical particles are indistinguishable. You cannot fundamentally distinguish one helium atom from another. They are just fundamentally indistinguishable. So the description of the many-body state must be symmetric under their exchanges. So what one can do, imagine you have a set of, you have this coefficient, and there's some set of quantum numbers that I just, for simplicity, denote by integers, right? These might be, say, quantum numbers of a harmonic oscillator in one dimension. But you know, these could be more complicated. For the sake of simplicity, I just consider integer numbers, right? So what this means is that this coefficient and these 1, 2, 1, 3, 7 are just the values that these quantum numbers take, okay? And what I see is that these quantum numbers repeat, right? Because we expect that in the ground state, the system will be in some state where many of these single particle states just repeat themselves, right? For instance, for non-interacting bosons, we expect all the bosons to be in the state of the lowest energy. So these, in principle, could all be the same. If there are some interactions, then some of them will be in excited states. So many of these, in principle, will repeat. So what I can now do, I can now use this property that allows me to interchange any of these entries to collect all the ones in the first spot, all the twos in the second spot, and so on. And since I only incur this plus sign, nothing really changes. So I can write this coefficient as C111111, and this occurs n 1 times. Then I put all the twos. This occurs n 2 times, and so on and so forth. Okay? And again, this is an identity. I haven't really made any approximation here. This is just the property of the indistinguishable set of particles. Okay, now comes the key idea that people like Fock and others realized. See, this description is hugely redundant because what we're saying here, we have 10 to 23 particles, and we're specifying each one of them in what state it is, right? And this is a hugely redundant description because they are completely indistinguishable. So the equal amount of information is contained in a much simpler notation in which we just specify how many particles are in state 1, how many particles are in state 2, and so on and so forth. And so we define a new coefficient by simply equating this to this quantity. Okay? So once again, instead of specifying the state of each of these 10 to 24 particles, we simply say how many particles are in state 1, in state 2, in state 3, and so on, and define a new quantity that simply contains that information. And in principle, there's infinitely many entries here because these quantum states, these quantum numbers would typically go to infinity, like in the harmonic oscillator, or momenta for a particle in infinite space. But nevertheless, typically only first few entries will have appreciable occupancy in a state that is close to ground state. Okay? And this is called occupation number basis. Any questions? Okay. So this is the first key idea. And what is now done, again, in this development, is that one rewrites the equation that one gets for these coefficients C in terms of equation for these coefficients C bar. And this, you can glance at these notes here, and you can see that this is somewhat complicated, but most of it is bookkeeping, right? There's no really fundamental new idea. It's just that you have to deal with all these indices, and you can manage them efficiently. So let me just give you a synopsis of what happens next. For reasons of convenience, one now defines a new quantity that we call f n1 n2 through n infinity t, which is simply this C with some combinatorial factor that makes things more convenient. And again, it's a technical point, so I will not really elaborate on that. But for completeness, I just follow the description there. Okay, and one can show that with this definition, so once again, this F is just the same as this C bar with this combinatorial prefactor. And if you're interested about the details, you can read from the handout. But anyway, one can show that this original wave function, psi R1 to Rn t, this is the original wave function that we're solving for, can be written in terms of these coefficients as follows. Can be written as a sum over n1, n2, and infinity, such that sum over I and I is equal to capital N of these coefficients, n1 and infinity t of phi n1, n2, and infinity r1, r2, rn. So this is so we have rewritten, there with sum over all the quantum numbers. here we sum over all occupation numbers consistent with the fact that we have n particles in total in our system. The coefficient is this function f, and this is a quantity that I define over here, phi n1 and infinity r1 rn. It's a so-called totally symmetrized wave function. So this is the completely symmetrized wave function of n particles. And what this means is that I just take this product as before, that's the same product as I started from, and I sum over all the quantum numbers consistent with these occupancies n1, n2, up to n infinity. And if you have trouble imagining what this is, let me just give you an example, because this is actually a simple quantity. So example of this completely symmetrized wave function, 1, 1, 0, 0, 0 of 2. So imagine I just have two bosonic particles, and I put them in state 1 and state 2. Okay, yes? Yes, thank you. So there's a normalization factor here, which I forgot. And yeah, it needs to be normalized. Okay, you can read the normalization wave factor in the notes. Anyway, so this object here, if we just have two particles, we put them in two lowest states, and it would look like this. 1 over square root of 2, this is the normalization factor, psi 1 x1, psi 2 x2, plus psi 1 x2, psi 2 x1. Okay? So this is what it means that it's symmetrized, right? It's completely symmetrized, so it implicitly takes care of the fact that these particles are indistinguishable. And it doesn't really make sense to talk about particle 1 or particle 2. It just makes sense, or all the available information is already contained in the fact that we have two particles. One is in state 1 and one is in state 2. Okay? Of course, for two particles, this doesn't save us that much energy to write it this way. But when you have 10 to 23 particles, then this becomes hugely more economical than specifying where these individual particles are. Okay, are there any questions at this point? So, okay. So the next steps that we skip actually massage the equation for this f in some intermediate forms that can get pretty complicated, and this is equations 124 and 125 in these notes, and I don't want to dwell on them very much, but let me advance to the next key point that makes this whole thing work. So the second key point is now introducing an abstract Hilbert space in which everything will suddenly simplify. Okay, and let me. So we introduce an abstract many-body Hilbert space in which we note the correspondence of this. So this will be the state vector in this abstract Hilbert space, and it will be in one-to-one correspondence with this many-body wave function that we started from. And similarly, we will introduce the basis in this space, which will be in one-to-one correspondence with these completely symmetrized wave functions. Okay. So the great advantage of working in this abstract Hilbert space rather than with some differential equations for these coefficients f n to n infinity is that the equations greatly simplify, and that's the second key idea in this development, that it doesn't really make sense to try to solve some hugely complicated differential equations for this, or nobody knows how to do that. But in this abstract Hilbert space, by introducing raising and lowering operators that manipulate these occupation numbers, everything simplifies to the point where this formalism actually becomes extremely useful. So we introduce this space, and raising, lowering operators often called also creation annihilation operators that act on these basis states. Okay, so the way we define this many-body state n1, n2, and infinity is simply as a direct product of single particle Hilbert spaces and for each of these guys, in analogy with the simple harmonic oscillator, we define raising and lowering or creation annihilation operators in the usual fashion. Okay, so we define So we define a set of bosonic creation annihilation operators by this commutation algebra. Namely, everything commutes except when you have a B dagger and B that correspond to the same state. Then these do not fail to commute by 1 on the right-hand side, and they act in the following way on these states, namely bk on nk just lowers the value of this occupation number. Similarly, b dagger k nk raises that same value. And these prefactors, again, are there in analogy with the harmonic oscillator, and they make everything properly normalized. And another important combination of the operators is b dagger k, bk, when it acts on nk, it simply pulls out the eigenvalue. So this, often we call n hat k, is the number operator. Okay. Any questions about this? So now, with these definitions, it turns out that the hugely complicated equations for this f can be simplified greatly such that I can write them on this remaining part of the blackboard. So after all these definitions, one can write the original Schrödinger equation in this new basis as follows. But now I'm working in the abstract Hilbert space. So the Schrödinger equation looks like this as before, but now I'm working in the abstract Hilbert space. And this Hamiltonian H is now an operator acting on in this basis, right? And it has the following form. It has two terms corresponding to kinetic and potential energy, and it looks like this: Ij, I, T, J, B dagger I, Bj. So this is the kinetic energy term, and then I have the potential energy term that looks like this: sum over I, J, K, L, I, J, V, K, L, B dagger I, B dagger J, BL, BK. Okay. And this is the result of the second quantization. What these guys are, these are just the matrix elements of the original operator written in equation 1 in the basis states of those wave functions psi, single particle wave functions psi. And in the following, we will show examples in certain situations how to calculate these for specific Hamiltonians. Okay? Any questions? So now it remains to discuss two things, namely what happens when the particles are fermions. There, things change a little bit. And then I will introduce one more concept, that of field operators, which will also be useful as we go along. So fermions, and I will do this quickly because there is just one new idea that I will quickly review. So for fermions, these coefficients have the antisymmetric property, namely upon exchange of two particles, the many-body wave function picks up an overall minus sign, which translates to this property on these coefficients. And from this, you can immediately see that when the two quantum numbers should be the same, for instance, if this is 1 and this is 1, then this is 1 and this is 1, and that corresponding coefficient must vanish, right? Because if they are both the same, then when you exchange them, nothing changes. The argument remains the same. Everything remains the same. But the coefficient is equal to minus itself, which is only possible when it's identically 0. So this immediately leads to Pauli exclusion principle. Namely, that this coefficient C is 0 if any EI is equal to EJ, meaning no two fermions can be in the same state, right? And we know that from elementary quantum mechanics. What that means is that once you go to this basis, when you reorganize these quantum numbers and you go to these F factors, N1, N2, N infinity T, then for fermions, these Ni's can only be 0 or 1, right? That just follows from this. At most, one particle can be in a given state. So when I organize them, say, in increasing order, then there can be at most one particle occupying a state with a given quantum number. Okay? So this is, of course, a fundamental difference between fermions and bosons. And it turns out that everything goes through here. One can write this expansion as before, except that the function capital phi is now completely anti-symmetric wave function, and it's given by the so-called Slater determinant. So as for bosons, psi R1 Rn T can be written as sum over N1 N infinity of F N1 N infinity T of this phi N1 N infinity X1 X N. And this is now completely antisymmetric wave function of n particles. And this is given by the so-called Slater determinant, which again you can look up in these notes. And if I were to give that same example for phi 1, 1, 0, 0, and so on, nothing would change except that I would have a minus sign between the two terms. Okay, similarly, it generalizes for more particles. It has to be now completely antisymmetric upon exchange to satisfy this antisymmetric property. Okay, so now with bosons, we constructed this abstract Hilbert space and creation annihilation operators to simplify things to this form. And we do the same thing for fermions, but it turns out we need fermionic creation and annihilation operators, which instead of these commutation rules, satisfy anti-commutation rules to, again, ensure the proper antisymmetry. So fermionic creation and annihilation operators are given by the following anti-commutation algebra, and we usually use letter C for these operators. And this curly bracket here stands for anti-commutator, namely A, B, sometimes also denoted as A, B, with a plus here, is defined as AB plus BA, whereas, of course, commutator is defined with a minus sign. So these fermionic operators have some interesting properties that follow from these defining anti-commutation rules. For instance, property number 1 is that CS squared is equal to CS dagger squared, and this is equal to 0. And you can simply see that from the second line. When you set both of them to be equal, right, then you get precisely this. And this just tells you that if you attempt to create or destroy two fermions in the same state, you get 0 because of the Pauli exclusion principle. You cannot have two states occupying the same, two fermions occupying the same state. What this means, for instance, is that C dagger S, when you hit the state with no fermions, you get 0 because you cannot create two of them. You can also show that C dagger S, well, let me just, since I'm using just a single state here, I don't need to put in any index. When I hit creation, when I hit the vacuum with the creation operator, I get a system with one state. When I try to hit it again, C dagger 1, then I get nothing. That's just a consequence of this. Similarly, when I hit a state with one fermion with the annihilation operator, I get a state with 0 fermions. And when I try to hit the ground state, try to annihilate a fermion that is not there, I get 0 again. And I also can define a number operator here, n, which is C dagger C, and it has the same property as for bosons, namely n acting on the state with n fermions just returns the number of fermions and doesn't change the state, but n can only be 0 or 1 in accordance with Pauli exclusion principle. Okay, any questions about this? So, except for these small modifications, everything goes through for fermions as for bosons. These look like small modifications, but of course they will have profound consequences for the ground state for many-body ground state of fermions versus bosons. And finally, one can do the same manipulation in this abstract Hilbert space to arrive at the final product, which looks exactly like for bosons, except that now we express everything in terms of fermionic operators. So the final result of this operation is this. And the Hamiltonian, well, this is kind of anticlimactic because it looks the same. but I will still write it for completeness. So it's the same form, just that it's in terms of these anti-commuting creation annihilation operators. Now, the important thing here is this ordering. So notice that ordering in the matrix element is RSTU. The last two here are ordered in the opposite way. And that just comes from the details of the derivation. It's the same for bosons, but for bosons it has no consequences because I can interchange those two operators with no penalty because of the commutation rules. For fermions, however, this order is important because if I were to exchange them, I would incur an overall minus sign, which would turn a nominally attractive interaction into repulsion and so forth. So one has to be careful about this. In some books, they put the order the same as here, and then they put an overall minus sign. Sometimes you see that, but again, I'm following this particular textbook. Okay, any questions about this? So this concludes the first part of the second quantization. Okay, so the last technical step today will involve the definition of field operators, which again are quite useful in practical calculations, and you see them everywhere. So we introduce them at this point. And I will do this for the case of fermions, but for bosons, the construction is analogous. So these operators C that we introduced, they can be thought of as creating or annihilating a particle in the state that is described by one of those basis, a single particle basis functions that we chose at the beginning. For instance, if our basis is plane wave states, then this creation operator C dagger creates a particle with momentum k and spin, say, up, right? Now, often it is useful to define operators like this, which instead create or annihilate a particle at a spatial point r, okay? And these are defined as follows, with sum over k psi k of r times ck, and the corresponding creation operator sum over k psi star, or sometimes we do, let me do it like this, r dagger c dagger k. So first of all, one has to carefully keep in mind the distinction between the wave function. This is just a single particle wave function that we defined at the very beginning, such as a plane wave, for instance. And this is the operator with the hat. So this is a field operator that creates that, or this one annihilates a particle at point r in space, and this one creates that particle. So these create or annihilate fermion in this case at spatial point now a slight complication arises when we have electrons that have spin. So with spin, our wave function psi of k r has two components, psi k r up, psi k r spin down, and we define this as psi k r with additional index alpha, where alpha takes values up or down, or sometimes we call them 1 or 2. And in case of spin-full particles, what we typically do, we define this a field operator for each spin separately, right? So that we have an operator that creates a fermion at spatial point r with spin up or down. So there's two sets of definitions like this for each spin projection, or sometimes we have different orbitals in a solid, and then the number of indices can grow. Okay. One can do some number of things with these field operators. For instance, one can define their commutation relations. Well, one can work them out. And they obey the following anti-commutation relations for fermions. Psi hat alpha r, psi hat dagger beta r prime. So you want to, for instance, work out this type of anti-commutation relation for these field operators. What you can do, you can just take these definitions, plug them in here, use the corresponding anti-commutation relations for these C's, and this turns out to be just sum on K, psi K R alpha psi K R prime star beta. And this is just a completeness. You can just use a completeness relation to deduce that this is going to be delta alpha beta delta R minus R prime. So this is just a completeness relation of your basis states. Similarly, one can deduce the other anti-commutators. For instance, psi hat alpha R, psi hat beta R prime, and this is going to be equal to 0. And similarly, the one where there is two creation operators. Okay. Another bunch of neat things that one can do with these field operators is to write the Hamiltonian in terms of these operators, and it looks like this. Okay, so this is the form of the Hamiltonian in these field operators. And again, I will not do that here, but it's easy to check. And the way you check that is basically by, again, substituting these definitions in here. You perform these integrals, and they can be easily performed because these are just integrals using the wave functions, and you get back the Hamiltonian written over there. Okay, and you can see that right away in this case. Once you plug in these forms, then you basically get a matrix element of this operator between the two wave functions, which is exactly what is the first term over there. Question?
If I take an arbitrary fermionic state and I just apply one of these the creation field operator, I've now got no guarantee that my resulting state is normalized, because if there's some CK dagger in my starting state, that will get that will get destroyed by the corresponding CK dagger. Is that a problem, or is that just something you have to live with, or is there a way to get around that?
Well, so these C's and C daggers have been constructed in such a way that everything stays normalized when you apply them to the state. So in terms of bosons, we have inserted these factors here because of normalization, right? Now, these field operators are constructed as linear superpositions of these C's, and the wave functions themselves are properly normalized. So as far as I know, there's no problem that arises using these field operators. Everything remains normalized when one is careful with these prefactors. Any other questions? Okay, so one very last formal thing before we finally move to some physics. So one can express an arbitrary operator in terms of these field operators by using the same recipe as we went through for the Hamiltonian. Of course, one doesn't want to go through all that lengthy derivation whenever one encounters a new operator. So there are some simpler rules, actually, that one can use. So arbitrary operator in terms of either CK daggers or psi daggers. Okay, and let me just give you the recipe here. So if the first quantized form looks like this, let's suppose this is a single body operator. Right? So this is an operator of the form of our kinetic energy up there high. So this is a typical single body operator, and this could be a density or a current or angular momentum or whatever operator you're interested in. Then the recipe for a second quantized is as follows. J hat in the second quantized form is just like for the first term in the Hamiltonian, R J S. One has to calculate the matrix element of that operator, and then attach the two creation annihilation operators. Or one can see that this is equivalent to writing it as integral d3r of j of r psi dagger r hat psi of r. Okay, and again, if you want to, okay, yeah, it's better to write it like this. I apologize for the confusion. Psi dagger r j of r. So it's easy to check that when you just substitute these forms, these definitions, you get back this part here. So these are identities, and we will see some examples for this in the following. Okay, so this concludes the formal development, and I'm happy that it's over. Hopefully this, however, gives you some appreciation for this second quantization formalism. In a typical book, it's kind of introduced basically in an ad hoc fashion, and then one keeps wondering, you know, where does it all come from? At least I did when I first learned about this. I thought this is neat. But I kept wondering for many years, you know, where does it come from? So it's useful to see that, although formally kind of lengthy and tedious, there's a one-to-one correspondence between the original problem that's now written up there high and this second quantized form, either for bosons or fermions, which looks like this. Okay? So unless there's questions about this formal part, let us now move on to the problem at hand, where we want to address this problem of electrons moving on the uniform background of positive charge, which is sometimes called the Gilliu model. Okay. So the problem that we want to address is defined by the following Hamiltonian. There's three pieces. So there's a purely electronic Hamiltonian, which contains kinetic energies of all electrons and their Coulomb potential, which is basically the Hamiltonian up there. Then there's a Hamiltonian of this inert background, positive charge, and then there's an interaction between the two. Okay, and let me write the three pieces in turn. So in the first quantized notation, H electron is simply given by what we had before, I equals 1 through n, pi squared over 2m plus e squared over 2, sum I not equal to j, e2 minus mu, Ri minus Rj divided by Ri minus Rj. Now, we will use what is known as screened Coulomb or Yukawa potential with this non-zero mu here, for the reasons that will become apparent shortly. Although the whole Hamiltonian is well defined as written, its individual pieces actually have some divergences for the true Coulomb interaction, which one can avoid by using this screened Coulomb and then taking mu to 0 at the end of the calculation. So as far as we know, Coulomb interaction is long range, no screening there, at least in free space. However, can anybody tell me under what circumstances one would get a Coulomb interaction like this? What would that mean in kind of fundamental terms? Speak up, please. Yeah, photon would need to have a mass. Is that possible? Could photon have a mass? Normally, gauge invariance prevents photon from acquiring mass. However, if your medium is a superconductor with broken gauge invariance, actually photon can acquire a mass, and then Coulomb interaction acquires precisely such form. So this is not complete fantasy, but we're using it here as a purely mathematical tool. And in the end, we will take mu goes to 0 limit at the end of the calculation. Okay, so this H background is simply the electrostatic energy of the uniform background. So using this coordinate x for the background positive charge, whereas r for discrete electron coordinates. As I said, the background is treated as a uniform continuum, but still it has this potential energy term that we need to take into account to avoid some divergences. And finally, let me see if I can squeeze the last piece of the Hamiltonian here. So the interaction between electrons and this inert background is of this form. It's just a Coulomb interaction. So basically the way to picture this system, we have a cube of side L, and in it we have a background of positive charge with density n of x, and inside it we have individual electrons at positions Ri, and everything is such that the total positive charge of the background and total negative charge of electrons balances out, so that together we get a neutral system, such as usual solid would be. Okay? And what we will want to do, in the end, we will want to take a thermodynamic limit where L goes to infinity in such a way that the densities remain the same, and take mu to 0 so that we get a true Coulomb potential. Okay, so as a next step, we're going to rewrite this Hamiltonian in a second quantized form according to the recipe that we just went through. So this is a good example. And the first step is to choose our basis states. And here, since we're dealing with electrons, so this is basis states for electrons, we choose a plane wave basis. This is the most convenient basis in this case. Namely, we choose wave functions like this. So this is the spatial part. This eta lambda is the spin part. And specifically, we consider spinors for spin up and spin down, 1, 0, and eta down is 0, 1. And they are mutually orthogonal. And we will deal with them in the following. And the second thing that I want to mention is that we use periodic boundary conditions. Namely, psi k lambda x plus r goes back to psi k lambda x, where r is any vector composed of multiples of L, right? So when I shift, say, along x by L amount, I get back to the same wave function. And then when we're interested in bulk properties of solids, we almost always use periodic boundary conditions because they minimize, well, they avoid any surfaces. So everything is bulk in that sense. And for periodic boundary conditions in a finite size L, this then puts a restriction on the allowed values of momenta. And the allowed momenta are of the following form. Ki, the three Cartesian components, are 2 pi over L times Ni, where Ni are integers 0, plus minus 1, plus minus 2, and so forth. Okay, and this is, I cannot have arbitrary value of k because I would not satisfy this periodic boundary condition. This basically says that I need to have an integer number of oscillations here before I come back so that the wave function remains single valued with my periodic boundary conditions. Furthermore, I will use the following notation. N will be my number of electrons in the system. Volume will be L cubed. And N will be N over V. And this will be the density. And I will have, like I said, the same density of my negative electrons and positive background. Okay, any questions about this? So it looks like I have run out of space. I need to erase something. And maybe I erase this. Yes. Oh, is there? Okay. Yes. Good. Ha. Good. Okay, nobody got this far. That's cool. We're breaking new ground here. I don't know if that's good or bad, but that's what we're doing. Okay, so we have three pieces of this Hamiltonian, and as we shall see, these two are easy to deal with because they ultimately, this is just inert background, right? So this is just electrostatic. All the action will be in this first piece here. So let's first get out of the way these two pieces. They will just contribute some constants, but again, we have to keep them around to avoid some divergences in our total energy. So we have to deal with them. So HB, this is just an integral, right? So what we do here, it's this piece here, and we're going to assume a constant density in our volume of this background charge, whose value is just there, capital N over capital V. So we acknowledge that, and we write this as E squared over 2 N over V squared. That's the density. And then what's left is just a double integral e to minus mu x minus x prime x minus x prime. And this is an integral that one can calculate. It's an elementary exercise in calculus. And the result is the following: e squared n squared over v 4 pi over mu squared. And here you can see right away that if we used straight Coulomb, namely mu is equal to 0, this would be infinity, right? So that's immediately obvious why we have to use this trick. This piece by itself would diverge. However, we will see that when we add all three pieces, this divergence will disappear for a neutral system. Similarly, one can treat this H electron background. And again, I consider the uniform background charge, so I can take out 1 power of n over v, and then I get I is equal to 1 through n integral d3x e to minus mu x minus ri divided by x minus ri. And although this contains electron coordinates, so in principle, this has some quantum variables in it, you can see that in a translation invariant system, for each electron coordinate Ri, I can just make a shift in this integral and absorb this Ri into this x. So it just disappears, and again, this just becomes an integral that I can calculate, and it's an elementary exercise in calculus. I just give you the result. And the result looks like this. And again, we have a mu in the denominator, so this term by itself would also diverge if we let mu equals to 0. Nevertheless, let us combine everything, and let's write the full Hamiltonian as follows. So we have this electronic part, which we still need to deal with. And then we collect these constants, and these constants look like this: 1/2 e squared n squared over v 4 pi over mu squared. Okay, so this is the Hamiltonian, and in the remaining 5 or so minutes, let us work out this electron Hamiltonian in the formalism of second quantization. So up there we have the recipe, right? Electron Hamiltonian has a single body term, which is this kinetic energy, and two body term, which is this Coulomb potential. And correspondingly, in order to write the second quantized form, we have to calculate the matrix element of the momentum operator and the matrix element of the of the Coulomb interaction. So let's start from the matrix element of T, which is the kinetic energy, and it has the following form: K1 lambda 1 T, K2 lambda 2. And let's just write it by definition, 1 over 2mv integral d3x. And I'm just plugging in the wave functions, right? Okay, so what happened here, this V is just a normalization factor on our wave function here. Sorry, I apologize. This should be V. This should be volume. So there's two of those, so I get 1 over V squared. Then I have my momentum operator, which has a mass in 2m in the denominator, so I take that out. And then I have a momentum squared, which is minus h bar squared Laplace. And this then acts on this wave function. These guys are just spin factors. This is independent of spin, so I can just calculate the product of the spin factors by orthogonality. And that results in the following form. So, okay, let me just write, and then I explain. H bar squared K2 squared over 2mv delta lambda 1 lambda 2 integral d3x e to minus, plus I k2 minus k1 dotted into x. So what has happened here? I have taken two derivatives of this exponential function, which brought me two factors of k2 times I downstairs, which is this factor k2 squared. Then I performed this product between the two spinners, this is just an orthogonality relation between them. So I will get 1 when they are the same and 0 when they are different. And what's left under the integral is just this exponential factor. And of course, this is going to be only non-zero when k1 is equal to k2. So I can immediately evaluate this and write the result here. H bar squared k2 squared over 2mv times delta lambda 1 lambda 2 delta k1 k2. And there's no volume here because, of course, when this is non-zero, then it's proportional to the volume of the system, so that volume just cancels that. And so I have the matrix element, and I can just use it in the construction of my Hamiltonian, and the kinetic term, therefore, looks like this. Sum over k lambda h bar squared k squared over 2m times delta lambda 1. C dagger k lambda C k lambda. Okay? Any questions? So I'm basically out of time. So let me just conclude by saying that in a very analogous fashion, one can calculate the second term. Again, it's just a calculation that is very similar to this. And one can write down the potential, sorry, the Coulomb potential. And let me just write it here so that I can use it when we get back next time. And it looks like this: E squared over 2V. And this one, since it's a 4 fermion term, is somewhat more complicated. I have more summations: K1, lambda 1, K2, lambda 2, sum over K3, lambda 3, K4, lambda 4, delta lambda 1, lambda 3, delta lambda 2, lambda 4, delta K1 plus K2, K3 plus K4, 4 pi divided by K1 minus K3 squared plus mu squared, C dagger K1 lambda 1, C dagger K2 lambda 2, C K4 lambda 4, and C K3 lambda 3. So this term looks slightly more complicated just because there is more quantum numbers available. Next time what we'll do, we take a closer look at it and we see how it can be simplified when it's combined with these guys here in the limit when mu is equal to 0. And we will discuss the properties of this interacting system based on this Hamiltonian. Any final questions before we adjourn? Okay then, thank you very much, and this is all for today.